Let's talk about some cognitive functions. So you might remember that our brain is lateralized. So here is our brain. And even though there are functions that are, more on one side or the other, one important thing to remember is that the left side of the brain controls the right side of the body, and the right side of the brain controls the left side of the body. So our left and right hemispheres are separate hemispheres, but they do exchange information. The main place where that information is exchanged is through the corpus callosum, but we also have the anterior commissure, the hippocampal commissure, and some other commissures that are too small to mention in this slide. So the corpus callosum allows our hemispheres to access the information from the other side. So as mentioned, so for example, the left hemisphere is going to be connected to skin receptors on the right side of the body and vice versa. But when we're looking at, so let me draw my gingerbread person, right? So the arms and legs, those are lateralized. But when we're looking at the trunk and the facial muscles, hey, I'm a human, right? Those are controlled by both sides. So in most humans, the left side of our brain is specialized for language. This is true for 95% of right-handed people, 80% of left-handed people. The functions of the right hemisphere are more difficult to summarize because, as I've mentioned many times, our brain is super complex, so we can't just pin one function on one part of the brain. Here we have a sagittal section of the corpus callosum, so we can see it from the side right here, and here is a view from the top. So if you were to just scoop out some of that gray matter and expose it, you would be able to see the corpus callosum connecting the two hemispheres of the brain. Yep. So another anatomical difference is in the temporal lobe. So the planum temporal is larger in the left side for 65% of people, and we even see this in infants. So even though the brain isn't fully developed, we'll still see that difference in mass. We're not the only ones who experience these differences and these specialties. So, in other primates, you'll see that they not only have hemispheric specialty, but you can also see hand dominance. So, the planum temporal is related to speech comprehension, and that is larger on the left side than it is on the right side. So, because of how light works, our vision goes into the opposite side of our retinas. So, light from the right half of our visual field goes into the left half of our retinas. Light from the left half of what we're seeing goes into the right half of both of our retinas. So, it's not based off of the eye, right? It's based off of the actual retina. So, in both eyes, as we'll see in just a second, what's in the left side is going to go to the right side of each retina and vice versa. So our left half of the retina is connected to the left hemisphere, but it's getting information from the right side of the visual field. Same thing with the right side. Our right half of our retina is connected to our right hemisphere, but it sees what's on the left side of our visual field. So half of our axons from each eye cross the opposite side of the brain at what's called the optic chiasm. So there is some crossing over of visual information. So we have something over here in the left visual field. We see that it's going to the right side of our retinas. We have something in the right side of our visual field going into the left side of our retinas, right? And we have this information from our left eye, which is going to the left hemisphere, from our right eye going to the left hemisphere. Information from our left visual field going into our left retina, our right retina, right? And then both of those, one is crossing the optic chiasm, one is staying lateralized, and that left information is going to the right hemisphere. So here are some olfactory bulbs. Here are our optic nerves that have been cut. Here's the optic chiasm. By the way, just so you know, chi refers to the Greek letter chi. I almost said X, but it's a Greek letter chi, which is also a cross. So it's you can think of that as literally a crossing or an Xing, right? Also, by the way, if you've ever wondered why it's Xing for crossing, it's because of the chi. So you learned something completely unrelated to biology just then. You're welcome. And then here's some little blood vessels. Oh, also, if you've ever wondered why it's Xmas for Christmas, you're like, what is that? What does that mean? Uh, some people think that it's because people are trying to remove the Christ from Christmas, which actually isn't true. Chi sounds a lot like Christ, right? You see that right there. So just an abbreviation. So next time you hear somebody say that people are being very rude to Christians, you say, actually, no, X is just a really nice abbreviation for Chi. And also, it's not even an abbreviation, it is that, right? So uh, I can, how many fun facts do you want? We could just stop talking about biology, and I could just give you fun facts. Do you know how many licks it actually takes to get to the Tootsie Roll center of Tootsie Pop? I don't know because I always bite it. Auditory information is a little bit different. So each ear sends information to both sides of the brain, and our brains compare input from both ears, but the hemispheres will pay more attention to the ear on the opposite side. So our right ear is going to be sending information to our left and right hemispheres, but my left hemisphere is going to pay more attention to the information from my right hemisphere and vice versa. As you might imagine, if you damage your corpus callosum, that's going to prevent the hemispheres from exchanging information in the same way that if you are in a major city and there is a bridge that you use to get to a certain part of that city, if something happens to that bridge, you can't get to that part of the city very easily, if at all, right? So there are some cases of epilepsy, which are occur when your brain is overactive. There's too much neural activity, and sometimes epilepsy can be treated with anti-epileptic drugs, also known as anticonvulsants. Sometimes people aren't responsive to drug treatments, so doctors will go into the brain and remove the focus, the point in the brain where the seizures begin. So if the corpus callosum is the focus, guess what will happen next? So if you can't remove the focus, or if there are multiple, or if the focus that you want to remove is essential for language, which is because language is so important to us as humans, it's not really something that you just want to cut willy-nilly. Sometimes we'll cut the corpus callosum, and that's going to limit the seizures to one area of the brain. And what sometimes happens is the seizures become less frequent. So the sometimes what ends up happening in epilepsy is activity and stimulation in one area will cause stimulation in another area, so it goes back and forth, which prolongs the seizure. But cutting the corpus callosum prevents that stimulation from traveling across hemispheres. So there are people who have had their corpus callosum split. So they have had a split brain procedure and they maintain their intellect. They're still motivated. It's not like a prefrontal lobotomy where they're kind of just dull and not really interested in the world and just sedated. They're still able to walk and talk, but sometimes they use their hands independently in a way that other people might see as difficult because what our brains are doing all the time is they're coordinating functions between the left and the right, right? Uh, but if I don't have the ability to do that coordination, then both sides are both working independently to try to get something done, right? So both are trying to do the same task, both are encountering the same problem, but one's controlling one side, the other's controlling the other side, and they can't communicate with one another. So if somebody who did not have their corpus callosum split saw the word hatband, then they would know that they saw the word hatband because hat went to this side and band went to this side. Now, if your brain is split, right, and you don't have the corpus callosum to take band and say, hey, right side of the brain, we saw band. Hey, left side of the brain, we saw hat, right? Then what's going to end up happening is both brains have only one bit of information. So if I asked you to, with your right hand, write down the word that you saw, right, you would write down band because your left hemisphere controls your right hand. Now, if I asked you to point at the object that you just saw with your left hand, well, what controls your left hand? Your right hemisphere. Your right hemisphere controls your left hand. It saw the word hat, so it points to the hat. So, because the two sides aren't communicating with each other, you're going to see that they don't have access to all of the information. So, some more facts about split brain persons. So, when stimuli are limited to one side of the body, that's going to affect our or one's understanding or ability to fully comprehend what you are seeing or experiencing. So, for example, because the left side of your brain is dominant for language in most people, if you see it in your left visual field, that object goes to the right side of the brain. So you're going to have a much harder time naming that object because that is a language skill, right? If you saw it in the right side, so it goes to the left side of your brain, then you'd have an easier time naming it. We do have those smaller commissures, so there are things that can transfer from side to side. But again, it's like that main bridge, that main highway. So if that is lost, then a lot of that communication is going to be lost. So in addition to our corpus callosum, we have the anterior commissure here, and we have our hippocampal commissures right there. So right after surgery, the two brain hemispheres are often in conflict. Uh, there's a really great story about to students being shown two sides of a Rubik's Cube, and one side maybe is blue and the other side is white, and they're both asked to say what side or what color the cube is, right? And one says blue and the other says white, right? Uh, Now, they can't communicate, or they're having trouble with this task because they're only seeing one side of the cube. All of us go, oh, there are colors on each side. So this side's red, this side's green, this side's blue, this side's white, then there's a yellow, and there's another color, red. Red is the other color. So the they go, because they're seeing limited information, right? They're going to argue. But when you can see the full picture, right, you can coordinate and work together on a task. So immediately after surgery, right, they're like these two people looking at different things where it's like, okay, well, I want to pick this up. The two hands might bump into each other, or there might be other issues because they just don't have that ability to communicate. But there's less conflict as time passes because the brain learns to use the commissures, right? It learns to use those smaller connections. So the hemispheres will show differences of opinion based off of how they are tested. So uh, One example of this, like these types of issues, would be looking at a self portrait. If you look at it in your right visual field, you would have an easier time identifying yourself in the portrait. But if you looked at it in your left visual field, you might have a harder time. If this last name looks familiar to you, you might recognize it because he was one of the authors of the Psychology 101 textbook that we often use here at Citrus, Psychology in Your Life. Uh, and he proposed the concept of the left brain as basically an interpreter. So the left side of our brain invents and defends explanations for actions, even if we don't really understand why we did something, right? So if I, decide to order pizza, right? There's no real explanation to why I decided to order pizza, but maybe my left side of the brain goes, well, I've been working hard and I just needed something that was quick and greasy and fun, because sometimes you just need to not eat healthily, right? And also, we know that our left hemisphere is important for speech. Our right hemisphere is great for understanding spatial relationships, but it's also helpful for allowing us to see the big picture. So it's more concerned with general concepts and the overall context of something. When we have damage to the right hemisphere, it makes it harder for us to perceive others' emotions. It's going to make it harder for us to understand humor and sarcasm, and we might also speak in a monotone voice. Any inactivation in the left or right hemisphere is going to cause a change in our functionality. Any inactivation in the left hemisphere is going to affect our ability to speak. Any inactivation in the right hemisphere is going to prevent us from feeling specific emotions related to traumatic or emotional experiences, but we'll still be able to describe the experience. So let's say I got robbed at gunpoint, right? If I had my left hemisphere inactivated, I could not describe to the police what happened, right? If my right hemisphere were inactivated, I'd be able to describe it, but I wouldn't feel the emotions, that like terror that I felt when it happened as I'm describing it. So you may have heard that some people are left-brained or right-brained. That is not how our brains work. Uh, if you haven't got that by now you know. But our functions are based off of the collaboration of both hemispheres of the brain. So people who are very creative. My cat is very right brained. You can tell because he's very vocal. Or I guess that would be left brained. He's also very creative. So when you any study, or usually it's like a fun article that's like, are you left brain or right brain? Right? That's not how our brains work. We don't rely more on one hemisphere than another. Most of the things we do require cooperation from both hemispheres. So again, me describing that traumatic event to the police officers, the left side of my brain is helping me process the actual words that I'm trying to say, while the right side of my brain is going to help me be in touch with those emotions and think of the big picture of what I'm trying to communicate. So our language is very complicated, right? If you think about what's going on right now, you're probably reading these words, right? And those words are letters and shapes that we've agreed correspond to specific sounds, which match words that we can say visually, right? We just decided that this sounds like this, huh, human, right? But also, we know that if I do this, right, that looks like a K. Sorry for my terrible Spanish, or not Spanish, cursive. But the just because it looks a different way doesn't mean that the meaning has changed, right? So we have a lot of things that we can do that still convey the like the same meaning. Even if I do something like this, you still are either thinking that I'm writing him, or you might go, "Oh, he's talking about humans," or but he's just saying it weird, right? So our language is a very complicated device that we have. It's a very complicated tool, and it's part of the reason why we've advanced so far. Our language compared to other species has a lot of what's called productivity. So we're able to improvise new combinations of signals to represent new ideas, right? So if if you think about like slang terms, you know, back in the day, if something was lit, it was literally on fire, right? But nowadays, with these kids, something that's lit means cool, right? Yeah, yeah, millennials and your technology and your texting, get out of here with that TikTok. But that productivity, that ability for our communication to change drastically, sometimes very quickly, is part of why humans are so good at being a very smart species. I definitely have the best words. I'm very good at using words. We are the best species. So, as you might guess, evolutionarily, right, the language that we have is just a modification of behavior found in other species. So we're just building off of things that already existed, and then we just made it better, right? So chimpanzees use language, but it's different than how we use it. They vocalize while breathing in. We vocalize while breathing out. Try speaking while inhaling. I tried to do it before I recorded this, and it was impossible. It was very hard. I can whistle while inhaling, but vocalizing while breathing in is very hard. So if any of you can do it, I will give you $1. Because there are a lot of you, so if all of you are able to do it, then I would be bankrupt real fast. Teacher salary. So We very seldom use symbols in new or sorry, they very rarely use symbols in new original combinations. So you're not seeing a lot of chimpanzee slang, right? Their symbols aren't productive, so they're not creating new ideas, and they're primarily using their symbols to request and not to describe. So when you have like a young child, 1, 2, as they start to like say words, they're saying words with intent. So if they say mama or baba, then they're saying that they want that thing, right? They're not just saying like, hey, look, there's my mom, and hey, look, there's a bottle, right? That comes later. So they're using language to request and not to describe, similar to what chimpanzees do. So here we see a researcher trying to teach this chimpanzee the English language. So there were little tokens that were arranged in order to communicate things to the chimp, and to a degree, chimps were very they were able to understand little bits of language. They're not reading Shakespeare, they're not freestyle rapping, but they can understand simple, direct commands. So, yes, no, do this, don't do this, place this here. Bonobos are a different type of monkey that are often used when we're trying to explore human behavior and its evolutionary roots. So bonobos are very similar in that they have a social order similar to humans. So they have typically male traits and typically female traits, and they interact very similar to how we do. When looking at their language, they can understand more than they can actually produce, and they use symbols and names to describe objects. And they can also request items that are not there, right? So if you have an apple in front of a bonobo, it could it's reasonable that it would be able to communicate, hey, I want that apple. But if they've had an apple a week ago and they love apples, right, it's pretty cool that they can formulate the idea of like, there was this thing that I had in the past. It's not here in front of me, but I can communicate that I want that, right? Uh, we take that for granted because we do that all the time. We're like, oh my God, I haven't had Taco Bell in forever. I need me some Taco Bell, right? By the way, if you use my code, you can get 10% off your next Taco Bell Grubhub order. So put in Professor T class 23. No, I'm just kidding. I'm not sponsored by them, but I could be. But they can request items that they have not seen. They can also use symbols to describe past events. So they could be like, had Taco Bell, sick, very sick, right? So stomach pain, brain pain, everything hurt. Now I'll never be sponsored by Taco Bell. And they can also make original creative requests. So let's say they've requested an apple before, they've also requested a banana before, they might request in the future apple and banana. Why not have it all, right? Check out this bonobo. What's up, bonobo? So the bonobo, as you might notice, is listening to some commands on a headphone or questions. And so the question might be, which one is the apple? And then the bonobo will select the apple or point at the grape, and then the bonobo will point at the grape. So bonobos have a very easy time understanding more complex language than chimpanzees do. So some of you might have grown up wanting a pet chimpanzee. Maybe you want a pet bonobo or a pet gorilla. Next time somebody's bullying you, just call your pet gorilla over. Problem solved. So with every study, when you're getting different results, then you always have to look at the possible explanations for why you got different results. So it could be that bonobos have superior language skills in comparison to chimpanzees, but it could also be that the bonobo training began early in language. If we feel like we've talked about critical periods before, but if we haven't, actually, that's more of a developmental thing. But critical periods, if you're not familiar, are a stage in our life where we're more receptive to learning. So that is why learning a language when you're very young is much easier than learning it when you're 35. Your brain is much more receptive to new information. And as it's forming those neuronal pathways, you're going to have a much easier time doing it. The earlier intervention with the bonobos might be the reason why they were able to gain language skills earlier. They were also able to learn through observation and imitation than just being taught. So the training method might have also been responsible for their language skills. It's not just primates who can understand human language, other non primates can as well. If you are ever feeling down and you need to pick me up, look up African gray parrots. They have a great ability to imitate sounds. I have a friend who has an African gray, and it will make like fart sounds, it will simulate doorbells, it will simulate different people's voices. So sometimes late at night, you'll just hear somebody say, hello, and you'll be like, oh, ah, oh, and then you're like, oh no, it's a parrot. So they have a great ability to mimic our sounds and also use them meaningfully to communicate things that they want, right? Dogs, as you might know, can learn to respond to many human words. So the left hemisphere responds to meaningful words. So sit, stay, want to go outside, right? The right hemisphere responds to intonation. So when we are excited, they get excited, right? Like, hey, hey, you want to go outside, right? They're like, oh, there's something good is happening, right? The right hemisphere is responding to the tone, which makes them excited, and then the left hemisphere is like, blah 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 outside. Oh, I love that, right? Uh, Fun fact: a lot of people think that cats don't respond to language. One thing that people say is like dogs know to respond to their names, cats don't. Cats respond to their names. They just often choose to ignore us. That's just a fun fact about cats. So you can actually see that they will respond to their names as and not other like meaningless words. But they will just like come running to us, wondering what's happening. They'll just be like, "Oh, I heard my name. Cool. Get my name out your mouth." So cats are very mean, but that's why we love them. This is Alex the African Gray. Oh, look at that beautiful little bird. I every time I see a bird like this, I get a little afraid, a little classical conditioning because my friend's parrot, every time he sees me, either bites me or digs his claws into my hand or like tries to attack my shoes. One time he almost pooped on my shoes, and we almost had to take it out to the streets and fight because you don't just poop on a dude's shoes, you know? So I would rather you key my car than poop on my shoes. You know, is that fair? Is that reasonable? But these birds are very smart. This bird had uh, been tested for 30 years, and there are some debates about like where his intellectual level is in comparison to humans, but he was about as smart as a 2 or 3 year old, but with better language skills. He could differentiate objects based off of color and number. So if you asked him how many blue, he would be able to say that there were one, two blue, right? If you asked how many green, one. A parrot. So cool. So, the more we study language in other species, the more we understand how language works in our brain. So, when there are people who have deficiencies in language, we can better understand the mechanisms behind it and better help them. So, we understand that our language is evolved from things that are present in other species, but also the more we try to define it and understand it, the more we realize that our concept of language is pretty ambiguous because there are lots of things involved in language. There's the production of sound or just the viewing of shapes. There is meaning, there is intonation, right? There's a lot involved in language, and that's just producing language. The ability to communicate with other people is another aspect because not only do we create the language, but it has to be properly interpreted by the recipient of that information. So, how did we evolve language? Well, language could have evolved from using gestures to communicate. When we see children using gestures early on to communicate, that's going to predict later onset of spoken language. So, what likely happened was sound plus gesturing with your mouth might have been a precursor to spoken language. So we're emotional and we're pointing at something that's dangerous and like gah 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 gah, and then someone's like oh ka 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 ka, and then we're like oh that sound, which I think I just said caca a whole bunch. Where that's what a saber-toothed tiger is, right? And then later around the campfire, we're like caca caca, right? And then everybody's like, oh, that's a saber-toothed tiger, right? So there are some brain language series. One is that it's just a byproduct of our overall brain development. So as other things were developing, that just coincidentally happened as well, or it evolved as a specialization. So it wasn't an necessarily an accident, but we started to develop it, and then because we it became useful, we developed it even more. Let's make it more confusing. People with a full size brain and normal intelligence can show severe language deficits. But people with impaired intelligence can also have normal language skills. So our brain and intelligence don't seem to be strongly related with our language skills. So it's not just our brain and intelligence that will determine our competency with language. So there's a disorder called Williams syndrome, where if you have several genes from your seventh chromosome that disappear, then that's going to lead to decreased gray matter uh, in your visual processing areas and other areas. It's going to People with Williams syndrome tend to have intellectual disability, so lower than average IQ, but they can still skillfully use language. So here is a drawing of an elephant by somebody with Williams syndrome. As you can see, that is not how most people would draw an elephant. So, you have to have the legs and stuff and the little elephant tail. So, that's showing intellectual disability. But describing the elephant doesn't seem to be an issue, right? They have big, long tusks. They can damage a car. It could be dangerous. When they're in a pinch, when they're in a bad mood, it can be terrible. You don't want an elephant as a pet. You want a cat or a dog or a bird, right? That is skillful use of language. So then we have the idea of language as a specialization. So Chomsky and Pinker propose that humans have a language acquisition device. Basically, that there's something in our brains that makes us very responsive to learning language. If you, we talked about critical periods just a moment ago, right? Children are able to learn language very easily, especially early on in their development. So why we develop language, it's very hard to say for sure. We can't just go back to early humans and just like ask their brains, like, "Hey, why are you evolving that way? What's going on there?" Right? It could be because of the long period of childhood dependency, right? Even 10, 11, 12, you're still dependent on your family. So that required dependence means that there's going to be more social interaction, and more social interaction is going to encourage the development of language. So here we go. We're talking about sensitive periods. Sensitive and critical periods refer to essentially the same idea. Critical periods refer specifically to a time where if a skill is not learned, it will never be learned. Sensitive periods are a little bit less strict. They refer to the idea that it's easier to learn something at a specific time in development. You can still learn it later, but it's going to be more difficult. So, early in your development, if you get no exposure to language, it can lead to permanent impairment. So the ease of learning a second language is going to differ with your age. Early on, if you're trying to learn a new language, you're going to have a much easier time with learning the pronunciation and being able to hear those differences, right, between like ere and erre, right? Sorry for butchering my ere. I'm very sleepy. Or did I butcher my erre? Wait, oh no, I can't do it anymore. What happened to my tongue rolling? It used to be so good. But if I were 7 years old, I'd be like, yeah, I'm killing it right now. And learning the unfamiliar aspects of grammar. Certain languages have different tenses and different rules on conjugating. So all those things are much easier to learn at an early age. Adults, however, have a much easier time memorizing vocabulary. So there is a little bit of a trade off. So there's no sharp cutoff for learning a second language, but if you're beginning after age 12, it's very unlikely that you'll gain fluency equal to that of a native speaker. So people who are bilingual at a young age show bilateral activity during speech for both languages. So you'll see that crossover from one side of the hemisphere to the other, of course, across the corpus callosum, of course. When you are learning a second language after 6, you're going to tend to only show left hemisphere activity. So, interesting to look at is also deafness and sign language, because sign language, even though it doesn't use the voice, uses the hand, and it's still very expressive. So deaf children who began sign language while young learn better than those who started later, which gives more support to the idea of a sensitive period. If you learn the spoken language early on as a child, it's you can still learn sign language later. And a deaf child who learns sign language early can also learn a spoken language later on. There are very rare cases of severe neglect in children where they are not exposed to language at all, and that does end up. You'll see that they have a very difficult time learning language later. As you might know from being in this class forever, a lot of our understanding of brain mechanisms comes from people who have had some sort of localized brain damage. You might remember Broca's area, part of the left frontal cortex, and any damage to that is going to result in language disability, specifically Broca's aphasia. So, if you remember, we have Broca's area right here and Wernicke's area here. And now it looks like it's like a little happy face. Oh, hey, I'm Mr. Brain. How's it going? Oh boy, I'm gonna have to tell you about language and how it works in the brain. Oh no, I'm fading away. Don't forget about Broca's area and Wernicke's area. Avenge me. That was dumb, and I apologize, but now you'll never forget Roka's area or Wernicke's area, so you're welcome. So when you have Broca's aphasia, also sometimes referred to as non-fluent aphasia, you might have difficulties in language production. So the actual creation, words, uh, sentence like that, the ability to speak fluently, right? That is Broca's aphasia. It's very hard to get the right words out. Regions in Broca's area contribute to language in distinct ways, which we'll talk about more on the next slide. And just because your Broca's area is damaged doesn't necessarily mean that all language will be gone, because speaking activates a lot of areas of the brain, not just Broca's area. So you still have your, somatosensory and motor cortices that are responsible for the coordination of the muscles in your mouth, right? Your tongue and all those fun things. So also, limited damage over time tends to get better because after damage, the brain starts to repair itself. So, as mentioned before, Broca's aphasia is going to lead to slow and awkward communication. This would even apply to people trying to use sign language. So, you might lose pronouns, he, she, they, it, prepositions of, for, about, above, below, and helping verbs. This is not an English class. I'm not going to list them all unless you really want me to. If you want me to list some helping verbs, jump down into that comment section below. On your way there, hit that bell icon. Make sure to subscribe. So you're really seeing limited language skills. Wernicke's area is located near the auditory cortex. It's also often called fluent aphasia because they can still speak smoothly, but there is impaired language comprehension and impaired ability to remember object names. So the the function in the brain where the like I'm trying to talk about aphasia, but I can't like remember the word necessarily. So I'm talking like the it's the because the when damage happens to the brain, it's uh like right that like if you've ever had that like tip of the tongue feeling where you can't find the word, that would be what it is. So they might have tried to replace the word with something else. When they see something, they might recognize it, but have a very hard time knowing what to call it. That would be Wernicke's aphasia. So, as mentioned, you're going to have articulate or fluent speech, except for pauses to find the right word. You're going to have difficulties finding that right word, which is referred to as anomia. A is a prefix, which means without. Nom is not just the sound that you make when you're having food, it refers to a name. So if you speak Spanish and you are familiar with the word nombre, right? Same Latin root, nom. So without names, so they can't recall the names of objects. Also, you might see poor language comprehension, so difficult time understanding what people are saying or writing or understanding sign language. So let's compare and contrast. Broca's aphasia, poor pronunciation of words. Wernicke's aphasia, unimpaired. Broca's aphasia, you're going to see mostly nouns and verbs. You don't have any of those words that help you make a sentence sound smooth and normal. But with Wernicke's aphasia, you're going to have a grammatically correct sentence, but sometimes nonsensical because the proper words might not necessarily be there. With Broca's aphasia, comprehension of words might be limited if the meaning depends on very complex grammar, but simple sentences, there's not going to be an issue. Wernicke's aphasia, language comprehension is going to be seriously impaired. So, dyslexia is a very specific impairment of reading in a person who doesn't have any other issues. So, it's not an issue related to vision. So it's not like something that could just be fixed by getting glasses. It's not an issue of motivation. So they want to read, but there's still another issue, and it's not a cognitive issue, or rather, it's not something that's related to like low intelligence. So dyslexia is more common in boys, and we have been able to find some genes that are linked to the development of dyslexia. And it occurs in all languages, but it is most common in English. So, in dyslexia, we might see abnormalities in the left hemisphere and also parts of the right temporal cortex that are larger than what we see in the left. So, if you remember, our temporal lobe is around here, but this would be on the right side. This is the left side that we're saying. So they might also have issues with auditory memory. So if you were to say something and then ask them to remember it, that might be an issue. And also impairments in eye movement. Different people are going to have different types of reading problems. So dyslexia doesn't look the same in everybody. So you can't just say no one explanation is going to work to explain all types of dyslexia. So in dyslexia, sometimes you'll see difficulty with the temporal order of sounds. So uh, when we listen to sounds or when we express sounds, we put them in a certain order to make sure that the correct order is communicated or the correct ideas are communicated. So sometimes what might happen is what's called a spoonerism. So the first two consonants of two words will get traded. So today you might be listening to this on a Monday, but luckily indoor phase it will be in 4 days it will be Friday. That will be an example of a spoonerism. So you're switching sounds, you're switching their temporal order, and that's going to change the meaning and interpretation. Sometimes it is you'll see abnormalities in attention, and so if you are focusing on a specific area, it's easier to focus your attention on letters that are slightly to the right of that visual fixation point. So we're seeing this issue in visual processing, but also in expressive language sometimes. So let's talk about the conscious and unconscious. So the there's something called the mind brain problem, which is the relationship with the mind and the brain. So, in case you're not familiar, the mind is kind of what a lot of people might think of as the soul. It is the functioning of the brain. So, if you think about the part of you that is thinking and going, like, what is Professor Thompson talking about? That is your mind. Now, you also have your brain, which is the organ. Now, we know that the brain is responsible for the functions of the mind, but it doesn't seem like our understanding of the brain fully explains everything that's happening in the mind. So, for a very long time, we had the concept of dualism, the idea that the mind and body are completely separate and don't affect one another. But Descartes proposed, the same guy who's like, all, I think, therefore I am. He was like, well, maybe the mind and brain interact at a single point in space. He suggested that it was the pineal gland. That is not true. But the more we saw things happen to the brain, over time we understood that more of the mind can be described as functions of the brain. So Descartes had this idea of the visual stimuli that we're looking at getting into the eyes and taking all these pathways to the pineal gland. Uh, that was wrong, but it was one of the first theories of how our eyes and our brain could correspond to our conscious understanding of the world. So, as you might guess, all philosophers and neuroscientists have agreed that dualism is not accurate. So, one, it conflicts with physics. So, if your brain isn't composed of matter or energy, how is it going to affect the physical world, right? If our brain and mind, like, so if my soul wants my hand to move, how is it going to control my muscles, right? So we unfortunately, Descartes, you were wrong. So then we have monism, which is a belief that the universe consists of only one substance, and there are some categories that are important to mention. One, materialism, that everything that exists is either physical or material. Mentalism, only the mind really exists in the physical world, could only exist if the mind were aware of it. So it's our mind that is helping to create reality. And identity position, that mental processes and certain kinds of brain processes are the same thing in different terms, right? So depending on what perspective we're looking at, they're the so if I'm looking at like the soul and like the mind, right? There's this functional process that is happening at the mental level, but also if I'm looking at it from a biological level, there's that same thing. So it's the same thing, but we can look at it at two different perspectives. So we have basically accepted monism as the most reasonable hypothesis for this mind brain relationship because experiences and brain activities are inseparable, right? You stimulate one part of the brain, you're going to see an effect on the person's behavior. And mental activity requires brain activity. If I'm thinking right now and you hooked me up to an fMRI or anything, you'd be able to see that there were changes in my brain as I start thinking, as I start trying to learn something new. So there are some easy problems and there are some hard problems when it comes to this. Easy problems: what is the difference between wakefulness and sleep, right? If we are asleep but our brain is still functioning and we're not conscious, right? What does that mean about us? Are we like if part of us is not conscious, if part of us is not as alert, but the rest of us is functioning, then are we still there? Are we gone? Like, what part of us is the real part of us? So that's a fun one. But also, how about a hard one? Why do we have consciousness at all? Right? Most animals don't think about things the way we do. We're thinking like, oh man, when I'm in 30 years, I want my grandkids to think that I'm a cool grandpa, grandma, right? And and squirrels aren't thinking about like their legacy. They're just thinking about immediate survival, right? So why do we have this ability to like view ourselves kind of objectively, like from the outside? Uh, there's no clear answer for that. Yeah, no. Whenever I get existential, my cat gets very upset because he's wondering about his place in the universe. And honestly, there are no good answers. We don't have any good answers. I'm sorry. How do you feel about that? Existential anxiety is a real thing. So consciousness can be difficult to define because it's very hard to observe. When we're trying to define it, we basically define it as if you can observe and respond to one stimuli, but there's a second stimuli that you do not respond to, then you were conscious for the first one and not conscious for the second one. So let's just say I'm giving a lecture and I talk about one topic and you're able to remind me or you're able to tell me what I just talked about. Now, during the second one, I talk about a different topic and you're not able to tell me what just happened. Then you were unconscious or not conscious for that second thing. So sometimes when we're trying to test consciousness, we might use masking. Masking can be regular masking or backwards masking, but essentially you'll present two stimuli and you're trying to see if they're aware of one of those stimuli. So maybe I show you a all black screen, and then for a brief second, I show you a circle, or maybe I show you the circle, then an all black screen. If you can recall the circle, then you were conscious when that happened. So sometimes we might get stimuli like this. Let's see if I can switch it up a little bit. There we go. And what's happening here is your eyes might, come on, cat, not right now. Not right now, cat. Can we not right now? Can we just not? So, as you were looking at that, what was happening was your eyes were looking at, we're both getting different amounts of visual stimulus or stimuli. I'm currently holding my cat like a baby so that he doesn't meow while I'm trying to record, just in case you're wondering what's happening in the background. So, because your eyes are getting information focusing on different things, that's evoking a brain response because what's happening is your eyes are communicating, or not your eyes, but the visual cortices are communicating and sharing that information. So, those gradual shifts in your visual focus are causing your eyes to sweep over the information, and that's causing both of your eyes, or rather, it's causing a brain response because of what your eyes are focusing on, which can be measured with an fMRI. I currently have a cat that's trying to resist my love right now. But cat, I gotta record a lecture. Cats are like babies. When you don't want them to cry, that's when they want to cry the most. And I'm recording a lecture, little buddy. Recording a little lecture. Recording a little lecture, buddy. So, uh, there we go. Something about eyes. There we go. Eyes, 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 eyes. There's a cat. He's digging his claws in places. So because your eyes are getting such different stimuli, like really try and get close to that, and like see what's happening with your eyes. That's really creating a lot of stimulation in both hemispheres because they're communicating and trying to make sense of all this information. But if you are processing this information, then that must mean that you are conscious. So we could set up a study for binocular rivalry where we have one constant stimuli over time, and then one in one eye you're getting this pulsating stimuli, and then we can measure that. So if a person reported seeing the stationary stimuli, then there were low levels of brain activity. If they reported seeing the pulsating stimuli, or sorry, stimulus, then there would be higher levels of brain activity. So consciousness is also tied into awareness. If you identify something as meaningful, you cannot be conscious or aware of it. So a lot of our brain activity is unconscious, but what's happening in our brain, even if it's not part of our conscious awareness, can still influence our behavior. So one theory of consciousness is that it is a threshold. So in order for something to meet our criteria of awareness, it has to activate enough neurons. And if enough neurons are activated, that's going to reverberate throughout the rest of the brain, making us aware of it consciously. If something fails to reach that level, then we're just going to not notice it. It's going to fade away. We might be subconsciously aware of it, but we're not consciously aware of it. Think about all the background noise that is in the world right now. You might not have noticed the hum of this recording. Or maybe you did and it's annoying you. I'm sorry. You might not have noticed your neighbors talking outside or birds chirping, right? Those things are below your conscious level of awareness. But once it stimulates enough of your neurons, you become aware of it. So there is a slight delay between when something happens and our awareness of it. If you think about it, information needs to travel through the brain for us to be aware of it. So there is a delay. Like what the present moment is actually like a fraction of a second after anything actually happens. So we're actually experiencing the past, right? Uh, and part of this is part of our perception of the quote unquote present moment is based off of assumptions. So if you see a dot here and then it fades away, and then you see a dot here, right? And then it appears here again, right? And then it appears here again. It's going to appear as if the dot is moving back and forth because that second position is going to affect our perception of what just occurred. We're not assuming that they are two different dots that are flashing on and off. It feels like there was one dot that was just here, but now it's back over here. If you are under anesthesia, you will lose consciousness. One, you'll see that there's decreased overall brain activity and there's decreased connectivity between your cortices and your thalamus, hypothalamus, and basal ganglia. So when you are recovering consciousness, when you're waking up from anesthesia, those areas are going to reconnect, and then you'll see increased activity in the cortices. So, if you are in a persistent vegetative state, we can still hook you up to an fMRI, and if you were asked to imagine playing tennis, we would still see increased activity in the motor areas of the cortex, similar to what we would see in normal subjects. Also, some people have been able to answer yes or no questions using this method. So, even though you're not conscious, right, your brain is still responsive. You can also use magnetic stimulation to activate a localized area of the brain, and then you can see how that activity spreads using an EEG or electroencephalogram. So you may have learned about attention and change blindness in Psych 101 when you were talking about sensation perception or when you were talking about memory. What we attend to is aligned with our consciousness. There is a lot of information that we miss just going through our days because our brains focus on specific bits of information. If something changes in the environment that we haven't been attending to, we might not be aware that that thing changed. So let's say we were in class one day and I was wearing a gold ring on my left hand, right? Now, you didn't notice that I was wearing a ring on my hand, or maybe you saw it, but you weren't really paying attention. If I went to the restroom and then changed my ring or took it off, then you might not have even noticed that that change happened. But our propensity for an intentional blindness is so great that we might notice or fail to notice huge things. If you have a few moments, feel free to do a YouTube search for change blindness, and you'll find lots of videos which can show how much you can miss, even if you're trying very hard to pay attention to things. So when we're looking at attention, there are two aspects to our attention and our processing. We have bottom-up processing, which is our immediate reaction to a stimulus. So, you're walking around, and all of a sudden a bee, pops out of nowhere and starts buzzing. You're getting all this new information, and it's grabbing your attention. We also have top-down processing, which is intentional. We have assumptions that we're making about the world, and that is going to color how we see the world. So if you're looking for somebody in a group of people, you're expecting to see them in that group. There's also a similar concept, which is the Stroop effect. So if I asked you, what is the color of the word that I just wrote? You might say red, although the color of the word is actually blue, right? The reason why you said red is because your brain, which it responds to language, reads it very quickly and says, that is red, right? But another part of your brain recognizes the color of the word, which is blue. And those two parts of your brain fight with each other, right? So if you are interested, look up the Stroop effect and you'll be able to see an example of this. And it's very hard for people to do this type of task because your brain is at war with itself. But this increases activity in the color vision areas of your cortices. So you're trying to respond to the color, not just the word. So deliberate top-down processing is based in the prefrontal cortex and the parietal cortex. We know that these are responsible for judgment and planning and making sense of lots of sensory information. Our ability to resist distraction varies among individuals. Interestingly enough, people who play lots of action video games can increase their level of top-down control. Meditation also improves certain aspects of attention. Inattention or neglect is the opposite of attention. So there's a term called spatial neglect, which is a tendency to ignore the left side of the body and its surroundings or the left side of objects. This can be associated with damage to the right hemisphere of the brain, and after a stroke, we might see these effects being more pronounced. A great example of spatial neglect, imagine you have a entire plate of food, and you go and you feel like your entire meal has been completed because you see an empty plate, but you've actually ignored all the food on the left side, right? So that would be an example of spatial neglect. These problems are associated not with the actual sensation, so visually they're seeing it, right? But it's actual attention. So they're not focusing on it. So you can see the entire letter and say what it is, but you might ignore the left half of a stimuli when asked to do something involving both sides. So here's a visual example of this. So there are all these letters that make up a word, and they're asked to cross out all the letters, but they only focus on one side. So that's spatial neglect. So there are ways to overcome spatial neglect. You can make sure that you pay attention to what's in the left side of your visual field. So if I know that there's food on, if I know I have a full plate, I can make sure that I'm looking at this side of the plate. You can look left while feeling an object in your left hand or hearing a sound from your left side. Or you can cross your hands in front of your body to decrease neglect to the left side. So here we go, crossing arms to the other side. That's increasing communication between the both sides. So, as you might know from being a human for so long, life is full of decisions and social interactions. These two things, which are very important to our lives, are two pretty new fields of research in neuroscience. So, when we're making a decision, we have several sets of cells that are responsible for helping us make that decision. One set of cells is going to accumulate evidence in favor of one choice, and then we have another that's going to accumulate evidence in favor of the other choice, and then we have a set of cells that is going to help us compare the two. So I'm very hungry, and I'm like, do I want to go to Taco Bell or Jack in the Box? And so I have my cells that say, hey, yeah, Taco Bell. And I also have my Jack in the Box cells. And then I have a set of cells that are helping me compare the two. You thought that we were going to go through an entire lecture without talking about rats? Oh, you're so young. You're so young. So there was a research study where we had a rat listening to a set of clicks, and the rat would turn his head in the direction with more clicks. So there are two parts of the brain that we are going to talk about in reference to this. One, we have the posterior parietal cortex, and it has two sets of cells that responded to the clicks on each side. And then we have the prefrontal cortex, specifically the frontal orienting fields, which are adjacent to the motor cortex, that have two sets of cells that keep score about which side had more clicks. So we have one or a set for each side looking at the click, or not looking at but responding to the clicks, and then there's also part of our prefrontal cortex that is keeping score and saying, okay, well, there are 7 on this side, 5 on this side. Oh, now there are 12 on this side, 7 on this side. Okay, I'm going to turn towards this side, right? So the parietal and prefrontal cortex are both measuring sensory information and then making a decision based off of that sensory information. And you might remember in chapter 12, we talked about the hippocampus and memory and how that's related to making decisions. In the spiral maze with a whole bunch of arms, having the hippocampus helps you remember which path you went so that you can go through in a systematic way. So we have our little rat friend right here. There are 4 clicks on this side. There are 7 clicks on this side. The parietal lobe is responding to the clicks, and the prefrontal cortex is making or keeping score, and then it makes a decision to go right. Sometimes we make decisions based on our values. We tend to learn which things have a higher payoff. That decision making is based in the basal ganglia. So if I know that, studying hard gets me a better grade, then I'm going to go, okay, well, I'm going to study hard. If I know that I can slack off and, play video games all day and still get an A, then my basal ganglia is like, yeah, let's play some video games and still get that A, right? Our ventral medial prefrontal cortex is going to modify responses in our basal ganglia. So when you see damage to the ventral medial prefrontal cortex, people are less sensitive to potential rewards. So if I was like, hey, if you answer this question, I'll give you $50. Normally, your ventral medial prefrontal cortex is like, yeah, a reward, right? But if there were damage there, you'd be like, oh, reward. I don't know. It also helps with confidence in one's decisions. So how decisive you are and how good you feel about the decision that you've made. Information is also relayed to your orbital frontal cortex, which compares expected rewards to other possible choices. Damage to the orbital frontal cortex makes it harder to stop making bad decisions. So, the book mentions the Iowa gambling task. Basically, what this task was, you are given a choice of 4 decks, and all those decks have a random number of very good cards that will make you win money and very bad cards that will make you lose money. So some decks of cards are lucky decks, right? They have more good cards and bad cards. Some are unlucky decks where they have a lot of bad cards and very few good cards. Most people, after playing with the decks for a specific amount of time, are able to figure out which ones are bad decks, which ones are good decks, and make better decisions, only playing with the good decks. If you experience damage to the orbital frontal cortex, you're going to potentially stick with a bad deck, even though you've had experience with it that's been terrible. So maybe the orbital frontal cortex is a reason why I'm still in a super toxic relationship. Thanks, orbital frontal cortex. I really need to learn that nothing's gonna change, and it's just gonna be this terrible forever. Just in case you're worried about me, I'm not in a toxic relationship. I'm single, guys, and it's okay. I'm just learning to value myself, and really, you can't love other people if you don't love yourself. Wait, you can love other people if you don't love yourself? That was just a lie that people told me to make me feel better about being single. Whew, oh boy. Now we're going to talk about love. Ooh. So, social neuroscience is a study of how our genes and chemicals and brain areas contribute to our social behavior. As mentioned before, this is a relatively new area of research, but it focuses on 2 very interesting topics: love and altruism. So being in love activates part of your brain involved with reward. So it feels good to be in love. We actually want to be in love. Brain activity when you are in love is similar to the feeling that you feel when you're on an addictive drug. So love is addicting. And if you think about it from a biological perspective, our genes want us to fall in love because if we do that, then we will have sex. And if we do that, I just hit a thing on my desk. My hand hurts. It's fine. If we fall in love, then we might have sex. And if we have sex, then our genes will reproduce, right? So love is a byproduct of our genes just trying to make more of themselves. when we see a picture of our loved ones, it's going to trigger our hippocampus and other areas of our brain responsible for memory. And love as a feeling is a combination of motivations, our drives and things that we want, emotions, our memories, and cognitions. You might remember our old friend oxytocin. Oxytocin stimulates contractions of the uterus during childbirth, stimulates breasts to produce milk, promotes maternal behavior, social approach, so how likely you are to approach somebody that you're interested in, and pair bonding in many mammalian species. So it helps you go, I like this person, I want to spend more time with them. Both men and women release it during sexual activity, orgasm. It has been called the love hormone, although a better term might be the love enhancing or the love magnifying hormone. Love is great. So we did some research on oxytocin. You can put it in a nasal spray, and when men viewed photos of their significant other, they would report much higher feelings of love and admiration than they did if they did not have the spray. But interestingly enough, it did not change ratings for other people. It just magnified the feelings for the person that they loved. Men in a relationship stood further away from an attractive woman when given oxytocin. So it enhances fidelity. So, for you people out there dealing with a cheating significant other, just slip a little oxytocin in their pancakes in the morning. Nothing wrong with a little bit of a pharmacological intervention. I didn't tell you that. You didn't hear it from me. That oxytocin just fell off a truck. So oxytocin can also affect our social relationships. So any group that we identify with is an in group, and any group that we do not identify with is in an out group. So let's say I am a big Clippers fan, right? So every time I see somebody with a Clippers jersey on, I'm like, that person's the homie, right? I see somebody with a Lakers jersey on, I'm like, I'm gonna rip that jersey off. Ooh, they make me so mad because they are the out group. So oxytocin increases our desire to conform to the opinions of the in group, but not to what people who are outside of that in group would say. It also seems to increase trust between people in the in group. So oxytocin can also increase our attention to potential dangers and heightens our reactions to threats from strangers. So, the current working hypothesis with oxytocin is that it increases our attention to social cues. So speaking of toxic exes, empathy, that's a thing. So civilized life depends on people helping one another. So I see somebody on the side of the road and they have a flat tire. I know how to fix a flat tire. I see them stressed out on a phone call and I go, man, it really sucks to have a flat tire. They seem very stressed. I pull over and I say, "Hey, do you need any help?" And they say, "Get out of here!" Right? Leave me alone. I've got AAA. Get out of here. So maybe they didn't have much empathy, but I was able to understand that that person might need help. So I stopped to try to help them. That is empathy, the ability to understand someone else's pain as if it were your own. I go, if I were stranded on the side of the road with a flat tire, I'd be frustrated because I might not know what to do. So let me see if that person is in the same situation that I am. It's not a thing that's unique to humans. There are all these wonderful videos online where you can see animals helping each other out. Like a elephant gets stuck somewhere, and then they all use their trunks to pull the elephant out. A little elephant family. So uh, it's not unique to humans, but empathy is related to our willingness to help, and that leads into the idea of altruism. So, altruism is the idea of doing something for someone else, basically selflessly. So, if I grade your paper and give you feedback, I'm not doing that because I'm selfless. I'm doing it because it's my job. But if there's somebody who's not one of my students who just randomly reaches out to me and is like, "Hey, I'm having trouble with this paper," and I say, "Oh yeah, sure. I have a little bit of free time. I'm happy to help you." Right? That would be altruistic. So people tend to be more generous towards those that they see as similar to themselves. This makes sense if you remember the whole in-group thing. If I think that you are like me, I'm going to help you. Uh, from an evolutionary point, this makes sense. There's an advantage if you're more generous to your relatives and not your strangers, right? If I have kids at home and I'm out working to provide for them, but before I get home, I've donated my entire paycheck to charity, then I'm not taking care of my kin. So my genetic line won't survive very long, right? People who are similar to you, we're going to assume are related to us. It lights up those same, like we just feel like if you've ever been in a situation where you're in a completely new place and then you see somebody with a shirt or like a bag that reminds you of like your favorite show or movie or band, and you go up to them and like you just feel like you've known each other for years because you have that similarity, right? We assume that people who have similarities to us are better people. That's just what we assume. That is what's referred to as an in group bias, right? We see somebody wearing a different jersey and we automatically assume that they're a scumbag. We see somebody wearing the jersey of the team that we love and we assume that they're the best person in the world. So, what determines how much empathy somebody has? Well, we know that some people have more than others, and a large part of it is culture and upbringing. If you are raised to see other people, no matter who they are, as genuinely good people, and you're raised to, volunteer and help others and go out of your way, then regardless of your biology or including whatever's in your biology, that's going to change how empathetic you are. If you are raised to only think of yourself and the most important people are your family and you never help strangers, then you're going to have less sympathy, right? So some of it is biological in frontotemporal dementia, where you're seeing degeneration in the frontotemporal lobe. Uh, you're going to see less empathy, a lower ability to care about the feelings and needs of others. So in frontotemporal dementia, you're also likely seeing damage in the ventromedial prefrontal cortex and the orbital frontal cortex, which, as you might remember, these are areas important for interpreting rewards related to decision making and other people's emotional expressions. They won't recognize or respond to others' reactions, including distress. So if I'm like, help, right? Most of us might go, oh, what's going on, right? They might not. So they're going to show little empathy. If you remember the trolley problem, right, where one person's over here and then there are five people over here, and you have the ability to save them if you just hit that little train switch. This is you over here. Uh, I know that's not five people, but I didn't want to drive five people, didn't have time. So if you hit that train switch, the train's going to go hit those five people, but now it's only going to hit that one person. A lot of us might struggle with this, right? They are more likely to kill the one person to save five because there's no emotional connection. It's just a purely logical decision. They also are going to show little interest in how others perceive them and are less likely to show embarrassment. So, a lack of empathy is sometimes related to sociopathy, or antisocial personality disorder. So that lack of interest in the perception that others have of you, and that lack of embarrassment, that lack of empathy towards the needs of other people. Frontotemporal dementia can look a lot like what a sociopath's brain would look like. So hopefully your frontal temporal lobes are working properly. Mine are working great because I feel like you might be exhausted after listening to this lecture. So that is it. We are at the end. I will talk to you soon for our final lecture. Time flies. Time flies.